As we said in the previous lecture, physical chemistry, the big three topics in physical chemistry are thermodynamics, quantum mechanics, and kinetics. And we're starting right out here in the very first lecture with equilibrium thermodynamics. Equilibrium thermodynamics, there are two other kinds of thermodynamics. Non-equilibrium thermodynamics divided into two parts, linear non-equilibrium thermodynamics and nonlinear non-equilibrium thermodynamics. But we'll just focus on this course, Chem 351, on equilibrium thermodynamics. Let's first set the stage here. Why does that appear? By defining a few things which will become useful. Let's first define what is known as a system, and then also talk about surroundings. So equilibrium thermodynamics deals with systems which may or may not be in contact with surroundings. So let's first define a system. This real big box here, this will represent the universe. That's that. And then what we do within the universe here, we carve out part of the universe and we'll define this thing as the system. And the part of the universe that is not part of the system we'll call the surroundings. So equilibrium thermodynamics deals with energy flows between the system and surroundings. Energy can be transferred to and from the system and surroundings, and also it has to do with the energy just of the system itself. So thermodynamics, energy going from one place to another, or within the system, what the energy of that system is. So thermodynamics deals with that. Equilibrium thermodynamics deals with systems that are at equilibrium, and we'll talk a little bit more in this lecture about equilibrium, but we'll define more precisely later on in the course exactly what we mean by equilibrium. Non-equilibrium thermodynamics, as you might expect, has to do with actually energy flows going from one place to another. So thermodynamics is the energy of a system at equilibrium, and perhaps more generally, it's the energy of a system at some initial state and the energy change at some final state. And these two states that we're looking at, the energy changes, are equilibrium at equilibrium. So it really doesn't say how a system goes from one equilibrium state to another, but it does tell what the energy difference is between those two states. Non-equilibrium thermodynamics will give more precise specification of exactly how things happen going from one state to another. Now, you probably recognize that I introduced what is known as a state. So let's talk about state. State usually refers to the state of a system. Now, in introductory chemistry, you probably talked about states of matter, solid, liquid, and gas, and that's one component of the state of an equilibrium system in equilibrium thermodynamics. But more importantly, the equilibrium state of a system is described by various state variables. And part of thermodynamics is specifying these state variables. Let's recall again from our introductory chemistry experience. Suppose we have here an ideal gas. And we could specify, if you look at states of matter, this would be the gaseous state of matter. But when we talk about thermodynamic state, we can specify what state this is in by specifying these state variables. Now, for an ideal gas, maybe you remember the state variables are P, V, T, and N. Pressure, volume, temperature, and number of moles. There's a relationship between these two, as called the state equation, or more generally or more familiarly, it's called equation of state. So the equation of state for an ideal gas is PV is nRT. So thermodynamics, this equilibrium thermodynamics this is a system here, it's an ideal gas, and we're describing the state of that system by these three variables, or these four variables, and there's an equation of state that relates those four variables. Okay. Now, variables often occur in natural intensive-extensive pairs. Now maybe you remember from introductory chemistry, maybe not, what intensive and extensive is. So let's go back and review that. So an intensive variable does not depend, can't spell here, on amount. An extensive variable, on the other hand, it does depend, I have to take handwriting lessons also, amount. All right, so let's look at some of these variables, these state variables for an ideal gas. Let's look at, say, pressure. Is pressure an intensive or extensive variable? Well, this is what I typically use in order to determine whether something is intensive or extensive. Suppose you have, say, an ideal gas, and this is at a particular pressure. You then clone that ideal gas system, and now you have an exact replica of that. Then you remove this barrier here. Is the pressure the same or not? The pressure is the same. So that means that pressure is an intensive variable. Let's do the same for volume. Let's take an ideal gas. It has a particular volume. And let's clone that system, exact duplicate. And now let's remove this partition. The volume has doubled. So that implies that the volume is an extensive variable. Okay, so we have extensive and intensive variable pairs, and there are natural variable pairs. One way to look at this, and when we talk about equilibrium thermodynamics and equilibrium more precisely later on, the intensive variable can be viewed as a potential, and the extensive variable can be used as amount. And these natural pairs, when you multiply these together, you get energy. So let's look at some things here. This might be too small if you're looking at this on a iPad or even on your phone. So let me, this is pressure here. Now I should probably use ink color black or blue, black maybe. So this is pressure and this is volume. Those are two naturally occurring intensive extensive variable pairs. Pressure is intensive, volume is extensive, and so when you multiply these two together, you'll get energy. Let's look at this. Here's force, that's an intensive variable. Here's length, that's an extensive variable. Remember from introductory physics, if you multiply force times length, you get energy. Oh, here's something perhaps new. We have electric potential, and we have charge, E, that's electronic charge. So here you have potential, and here you have charge, and you multiply those together. If you move a charge through a potential, you do work or energy. Oh, here's something even cooler. We talk about electric potential when you have charges moving through some potential. Here's a chemical potential, and here's the number of moles. That's a natural intensive extensive variable pair, and you multiply those two together, you get energy. So if you remove, this is sort of abstract now, but we'll talk about it more detailed later. If you remove a certain number of moles through a chemical potential, you're going to do work or energy. And here's even cooler. This is temperature That's an intensive variable. If you take two systems at the same temperature, you put them together, you'll still have the same temperature. What's the extensive variable that goes along with that? Is entropy. Entropy, maybe you remember from introductory chemistry, it has to do with heat transfer from one place to another, or it has to do with probability of having a certain state. But in equilibrium thermodynamics, temperature and entropy are naturally occurring pairs, and you multiply these two together, you'll get energy. So let's look a little more detail about potential and amount. Okay, let's change back to, say, yellow. Yeah. Okay, so suppose you have a potential, and let's use electric potential. So this is psi, so this would be electric potential. And this is some coordinates, some Cartesian coordinate x. And suppose you have electric potential that looks like this. And now we have an electron here. That's a charge. The electron sees the same potential no matter where it is, and so it'll just sit there. There'll be no driving force for it to go. And in fact, we'll see this is one of the definitions, more precise definitions of equilibrium. There's no gradient in potential. Let's now look where you have a gradient in potential. Here you have electric potentials high there and low there. And let's put an electron here at this particular position. What's going to happen? The electron is going to go from a high potential down to a low potential. And as it does that, it does work. So it moves from one place to another. This essentially is how a battery works. There's a potential difference across a battery. Electrons like to go from high potential to low potential. So there you go. So we'll look at those in more detail. But that's another way of looking at variables, as one variable, the intensive, is a potential, and then you have something extensive, which depends on amount, and those two will give you the amount of work. And these variables occur in terms of natural pairs. All right, so let's go to the next slide here. Let's talk a little qualitatively about equilibrium. We'll have more quantitative definition later on. We just talked about no gradients in potential, and therefore no flow of corresponding extensive variable. So here we did it for electric potential. This will be an equilibrium state. But when you have a gradient in potential, you have a non-equilibrium state. All right. So that's one way of looking at equilibrium. Another way of looking at equilibrium, perhaps familiar with your study of thermodynamics and introductory chemistry, is no change at infinite time. So let's look at that. Suppose you have, say, a chemical reaction. Let's write a chemical reaction. A plus B goes to C. And this will be time. And let's start with some concentrations here. And say initially this is equal to 0. And actually let's make this an equilibrium reaction, so it goes both backwards and forwards. Initially this is the concentration of C as a function of time. Initially it's there. Now as the reaction proceeds, C will be produced, but after a particular time, you get no change in the concentration of C. So another way of looking at equilibrium is things change, but if you wait long enough, things don't change anymore. And out here, you're at equilibrium. Okay. And then a third way of looking at equilibrium is, again from introductory chemistry, free energy is at a minimum at constant temperature and pressure. Now we'll have lots more detail than we had in introductory chemistry about free energy, but let's just review that. we'll draw it this way. Here is free energy, which we'll denote by the symbol G. That's free energy. Sorry that. So this is G, free energy. And this will be, let's do for a chemical reaction, this will be the progress of the reaction. So let's again use A plus B, and that will be in equilibrium with C. And suppose that you're not at equilibrium, you're over here. So you suppose you have more reactants than you should have in products. So what you do, the reactants will go down and the products will go up, and pretty soon you'll go down here. But then, if you now go past equilibrium, now you have more products and you have reactants. The reaction will go backwards. So over here you have more C. Over here you have more A plus B. And so A plus B will go to C. Here C is too much. Right here at the minimum of free energy you have equilibrium. So that's another definition of equilibrium. These free energy is at a minimum. That's at equilibrium. So that particular ratio of concentrations equal to the equilibrium constant will be the concentrations at which the system is at equilibrium. All right, so you probably remember these from Intro Chem. And this will be new, perhaps new, in Chem 351. All right, so that's, I hope, has set the stage for equilibrium thermodynamics. The next part of the first lecture will dive right into the first law of thermodynamics.